Good morning, everyone. You're welcome to another series of this chemistry class. Today, I'll be discussing on electrochemical series, that is the arrangement of electropositive elements and electronegative elements as highly asked by students for us. Now, this is response to your question. Now, electrochemical series is coined out of the arrangement of electropositive elements. I mean metallic oxides, metals generally. Now, what are metals? Metals are conversant with lacklusteredness, that brightness. They are conductors of heat and electricity, and they have what? They have an oxidation number or state that are stable, +1, +2, thereabouts. They belong to the group 1 through group 3 elements, the alkali metals, the alkali earth metals. These are electropositive metals: sodium, potassium, copper, aluminium, magnesium, tin, gold, silver, mercury, lead. These are all metals, and they are all electropositive elements. Now, when we talk about the non-metals mostly we're looking at group 7, group 6, period 5, 6, 7 as well. What do I mean by that? Elements that are unstable in their outermost shell electronically are mostly non-metals. And what are their attributes? They do not conduct electricity, they are not lackluster, they cannot be drawn into sheets and ions, and most times they are unstable. So these are non-metals, and mostly we put group 7 or group 8, mostly water formers or halogens, best called in chemistry. These are what water formers? The fluorine, the chlorine, the bromine, the iodine. All of those are water formers. They go through a process in chemistry that is called a substitution reaction. They move in relationship with water, and once they relate with water, they are what? They are forming either common oxides, could be acidic, could be basic oxides, could be amphoteric, both acidic and basics. Now, let's quickly talk about this electrochemical series. I do take students and tell them electrochemical series are coined in carbon could magnet alizone from Zeki parabolically, or could hand Agnes August. I've just completed the series of electrochemical series. Carbon for potassium, albium for sodium, carbon could is for copper, Cu, magnet is magnesium, Agnes is mercury, hydrogantium, Latinized name. From sinking, from I use is ion 2 or ion 3, best according to its oxidation state. Then alizone is aluminium, zone is zinc, parabolically is lead. So these are what? Hydrogen, or Agnes August means argentium, that is silver, and what we mean by urium for gold, Au, best put. Now for electronegative elements, I said in some northern country bromate hot free, meaning I in some is for iodine, naughty is for nitrogen, could be nitrogen 3, could be nitrogen 4, could be nitrogen 5 oxide. Some naughty countries, some is sulfate 6, sulfate 5. Country is chlorine, bromate is bromine, and each is what? Is iodine, hot free. OH, hydroxyl, that completes the electronegative series. Now, we can't go into the electrochemical series without a student of chemistry knowing at least the first 50 elements of the hand is necessity, so that when you are asked the mass number or the atomic number, you'll be able to divine what mass number are, what atomic numbers are. Now, mass numbers are the addition of the proton and the neutron, while atomic number is just the protons alone that is present in an element. So it's the protons that determines the atomicity of an element, that is its arrangement according to the periodic table that Dmitry Mendeleev gave us in 1746. A Russian scientist gave us the periodic table that is telling us that horizontal rows are groups and vertical columns are periods. Then he did the splitting. Before then, a lot of scientists have worked on it. J.J. Thomson, Rutherford, Millikan, John Dalton's theorem, that he gave postulation about atom not being the smallest particle of an element, that if it's not an ordinary chemical reaction, if it occurs in a nuclear reaction, atoms is breakable when heat is introduced. That's why you have the proton, the neutron, the electron. The proton is negative, the neutron is neutral, all in the nucleus, and the electron is the one moving around looking for stability outside with the negative notations. So having done all of this, students must know the first 50 elements. I do encourage my students to know at least first 50. If you can take it to 70, that betters it. So it's not like I'll ask you to do it and I'm not doing it myself, which I'm going to do now. So we have hydrogen, helium, helium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, gallium, germanium, arsenic, selenium, bromine, krypton, rubidium, strontium, yttrium, tritium, zirconium. That's first 40. You could do more than that. We have niobium, molybdenum, technetium, ruthenium, rhodium, palladium, tin, cadmium, indium, on and on like that. So all of this is best to know so that when you ask an oxidation number or oxidation state of an element, you'll be able to fix it. Oxidation state is the power of the element in reaction according to its reactivity or electronic configurations. So all of these questions can be answered when you're well grounded in your atomic mass number and mass numbers and their empirical formula and relativity ratios. What are the dilution rates? What are the dilution theorems? How are they being dissolved? We did something elementary science. We said when a solute, which are solids, react with a solvent, which are liquid, it gives a solution. What kind of solution? Usually gives two types of solution, homogeneous and heterogeneous. Homogeneous solution means solutions of the same kind. Heterogeneous solution means solutions of different kinds. How do we differentiate homogeneous from heterogeneous? Now, an homogeneous solution is a solution that the solute dissolves totally, that there is no traceable or any particles that are found underneath it when it's being dissolved. That's total dissociation. That's what we call it in chemistry. But the one that dissolves and we have particles at the depth end or at the bottom of the beakers or any apparatus you choose to use, those ones are not homogeneous solutions. They are not of the same kind, so they have different kind. We call them heterogeneous. So condiments are not homogeneous, they are heterogeneous. When you get back from the school and everywhere is hot and you decide to take cassava flakes and water, you had sugar, you had milk, you had Milo, you put granules, you just want to mix things up and tick up everywhere. So that's condiment. It's an homogeneous mixture. They are constituents, they can be separated. So another thing is knowing the differences between the mixture and compound. So compounds and components, mixtures are constituents. Components cannot be separated by a physical means. Why? Mixtures are separated by a physical means. So that's another thing you need to know. Mixtures can be separated by a physical means. Compound cannot be separated by physical means because it's coming together, it's by what we call a chemical reaction. So when two or more elements combine together to form a compound, they are chemically combined, and that is the definition of a compound. While mixtures are constituents that are being placed together. So in mixtures, it's retrievable, you can get it, it's a physical change process. You can get back what you've mixed. In compound, you can't get back what you mean, what you've gotten, but you will get a new product. If I decide to burn an exercise book, I will not get back the book like the pop, but I will get ashes in return. So that's the chemical process. When I dissolve cement, or I decide to dissolve lime, what's it called? I used to just dissolve quicklime, this extract of lime orange. So these are real life situations that attest physical and chemical changes, and all scientific laws have to be applied. So if your laws are not applied, that's another thing we have to look at again. Charles' laws talks about everything you do in your kitchen, in the oven, you heat, you ovenate, you fry, everything in the kitchen obeys Charles' law. Volume, temperature, relationship, pressure are kept constant. When you decide to blow a balloon or a deflected tire is to be inflated, you're using what we call the Boyle's law. The pressure and the volume, temperature is kept aside. When all of these parameters are combined, the pressure, the volume, and the temperature is being combined, they are talking about what? The general gas equations. Then when it's ideal, the number of moles come into place with a constant rate of reaction. So I believe I've answered for us. Meet you in the next session. Thank you very much.